We'll get started. Thanks everyone for coming. So I think Devin would be giving this introduction since he and Mark are going to be talking about some work to do together, but he is highly immobile now at the back of the room, so I'm here giving you, this is going to be my, thankfully I've introduced so many talks this term, I'm so happy this is the last one. But we're delighted to have here Mark Hertzberg from Tufts, who, let's see, in terms of professional background, let me see if I get this right. He's from Sydney originally. He came to MIT for grad school and then was a research fellow at both Stanford and MIT, is that right? And then has been at Tufts for the past few years and works on a number of aspects of theoretical cosmology. And so he's going to tell us today about the accelerating universe and relativity. Okay, great. Yeah.
Oh, that's probably not it. Did I do? Okay. Can everyone hear me? Okay. All right. Great. So thank you for the introduction, and thanks for the invitation to be here. So, so in this talk, I want to talk about this accelerating universe and particular relativity. So let me sort of begin by mentioning what we might call the standard cosmological model that has been put together, where if you consider the pie chart of the energy budget of the universe today, about 5% or so is ordinary atoms, so ordinary matter, and about 25% or so is dark matter, which presumably is some new kind of particle that happens to be essentially electrically neutral and is difficult to interact with. And then the residual 70% or so is some kind of dark energy. Okay, and that's more or less things today. If you think about the evolution of these ingredients, as you go back into the past, the percentages are rather different. So if you go all the way back, say, to the Big Bang, where perhaps quantum fluctuations were rather important, there may or may not have been a phase of so-called inflation that I'll come back to. We do know that whatever happened at some point, and about when the universe was 380,000 years old, there was, the radiation that had been produced in this early era got emitted. So there's this early hot era, and when electrons combine with protons to make neutral hydrogen, this light can get emitted, and that's the cosmic microwave background radiation that we can look for today. And then in this intervening era, there's the so-called dark ages, and eventually stars are produced, and so on, in galaxies and so forth. And as the universe keeps on expanding, the densities of these materials are getting smaller and smaller as the universe expands. But then there's some period here where there's some type of so-called dark energy, whose energy density appears to be fairly constant, and then we enter an era where that dominates. Okay? Now one can look back all the way to this era when it was 380,000 years old, so for example from the Planck collaboration, and one sees a sky. So if we look at the whole universe around us, there's sort of a two-dimensional sphere that surrounds us of light coming from every direction, and these red and blue indicative of different temperatures in the sky. So the temperatures are almost the same number at the 10 to the minus 5 level. Okay, so the universe is almost perfectly homogeneous and isotropic, but then there are these fluctuations, which are incredibly important. And for example, one can quantify the strength of these fluctuations on different scales. Okay, so if this was, say, in one dimension, I might do, say, a regular Fourier transform. But when you have a two-dimensional sphere, you decompose it in the spherical harmonics. And then one can look at the strength on different scales, okay, the amplitudes of each spherical harmonic. And it looks like this, again from Planck data. And so what you have here as you go to the right is basically looking at small angular separations in the sky. And as you go to the left, you're looking at very large angular separations. Okay? And one sees these sort of peaks and troughs in the intensity. And this is fairly well understood. Okay? So in fact, very well understood. So this early era here, if we go back a second, there was this radiation and matter-dominated era where the material has lots of pressure, so you get pressure waves or sound waves in the universe in this, what's originally some kind of plasma. And you have to do a careful calculation, but certain modes that are undergoing oscillations are resonant, and so you get some kind of peak, and certain modes are not non-resonant, and you get a kind of a trough, and so on, and it has this shape. And the red is the data, and the green is the theoretical prediction according to this sort of standard cosmological model. And you see it agrees remarkably well. As you go to larger and larger scales, you're looking back to, you're affected by things that were on really large scales, which potentially were set up by inflation that actually drags things to really large scales by an exponentially expanding phase, an accelerated phase. And it predicts a spectrum that's roughly flat here, and that's roughly what we observe. Okay. So broadly speaking, this is compatible with the idea of early universe inflation, an early phase of accelerated expansion. Okay. Now you can take these, what are very small, 10 to the minus 5 level fluctuations here in the CMB, and as well as there are similar fluctuations in the matter itself, and evolve it over time. And so here's a simulation of that. Those 10 to the minus 5 sort of fluctuations grow essentially under gravity. So this is basically just the matter of the universe, primarily dark matter in the standard cosmological model. And they just evolve over time, and then structures emerge. Okay? Galaxies emerging, clusters of galaxies, with certain kind of structures between them, and so on. And the arrangement or the pattern of these, you can predict at least statistically, given you know the sort of initial conditions, if you like. And then you can compare this arrangement from a computer simulation to observations. Okay, so for example, the Sloan Digital Sky Survey, mapping out the distribution of galaxies on very large scales here. And overall, it's in broad agreement. Okay, the theoretical prediction from those simulations and the observations of the actual set of huge numbers of galaxies that have been mapped out. Okay. So furthermore, if we think about, say, supernovae at high redshift, okay, so as you look further back, the light that comes to us is affected by how the universe is expanding. And if it accelerates, the light will come to us with a certain kind of reddening as the wavelengths get longer, or a different fashion if the universe was not accelerating. And this is broadly in agreement with an accelerated universe, and roughly compatible with so-called vacuum energy, where the energy density is more or less constant over time. In fact, well, vacuum energy is literally constant over time. Okay? And there are various pieces of evidence for dark matter. So not only is dark matter influencing this distribution, and so on, if you get down to not only on cosmological scales, where the evidence is rather clear, on smaller scales, it's actually somewhat more, even more well known that dark matter is important for, say, individual galaxies. So if you look at the velocity of a galaxy as a function of how far you are out, without any dark matter, you would predict a curve that looks like this. Okay, so as you go out, you'd expect smaller and smaller speeds, similar to how, say, Pluto is orbiting the sun slower than, say, the Earth and so on. But the observations look like this. And again, this is compatible with there being dark matter, which, if it fills the galaxy, alters, if you just solve Newton's laws of gravity, it gives a different distribution, a different velocity versus radius. Okay, and so I've given you a flavor for this the following point, that there's a kind of concordance, if you like, of observations on various scales, okay, going to larger scales on the left and smaller scales on the right, from cosmic microwave background observations into large-scale structure surveys, looking at clusters, lensing, the so-called Lyman alpha forest. When you look at the spectrum from distant sources, their redshifting is affected by how the universe expands and so on. And again, a broad agreement, okay, from various different observations. In fact, if you squint, you may notice there's a kind of some sort of wiggle here. And that can be replotted like this, with appropriate rescaling. And indeed, the matter so-called fluctuations, so this is roughly galaxies, how many galaxies there are, their typical separation or their correlations, have peaks and troughs. And that peaks and troughs is connected to the peaks and troughs I mentioned earlier for the light itself, for the cosmic microwave background radiation. That undergoes the peaks and troughs because of these acoustic waves. And so does the matter. Okay, and you can see it here. So again, a picture of consistency. But this you're measuring at much later times, okay, rather than the 380,000 years when the universe was very young. This is at much later times. And so the kind of scales here, the typical, say, distance between, say, a pair of troughs or a pair of peaks, is sensitive to how the universe has expanded since that very early time. Okay, it's going to redshift, so-called, by some huge amount from 380,000 years to closer to today. And so that distance there is sensitive to how the universe expands, and in particular it's sensitive to having a late time accelerating universe. Okay, so that's a quick review of the picture. And so again, there are these two eras, but if you look more carefully at the numbers associated with these accelerating phases, they're a little strange. Okay? So this late time universe, okay, where we have this dark energy domination, if it's this so-called vacuum energy, the vacuum energy is something whose energy density is a constant over time. Okay? And if you look at its value today, it was this sort of 70%. So its vacuum energy density is a factor of 2 or 3 times the matter energy density. Okay, and that might sound a little boring, except for the fact that if you go back in time to the much earlier universe, the matter energy density, as particles were closer together in the early universe, that density was much, much larger. If you keep going back, it just gets larger and larger and larger by orders and orders of magnitude, depending on how far you go back. But vacuum energy stays fixed. Okay? And so, in fact, if you go all the way back towards the Big Bang, so you go back to where we think physics more or less ends, say the so-called Planck era, you could ask what percentage of the universe would be in vacuum energy back then? Okay? Well, the value turns out to be 10 to the minus 120 in the Planck units. So that's the percentage back then, 10 to the minus 120 times 100 if you want to convert it to a percentage. That's the fraction. So then it's ridiculously small. And we happen to be in an era where this miserable little 10 to the minus 120 from early times perspective has stayed constant while everything else was falling. And we live in an era where this other stuff has fallen to the point where these are comparable. So that seems a little peculiar. And then the flip side of that is what happens if you go into the future. Into the future, this thing just keeps dropping, and this guy will completely dominate. So the further and further you wait into the future, this percentage will not be 70%, it will go to 99.9999% as you keep waiting further and further. Okay. So this seems a little peculiar. If you look at the early time inflation, this, again, some other accelerator phase, the numbers are not so extreme. There's no 10 to the minus 120, but the energy density, it turns out, to get it to work has to be less than 10 to the minus 10 in the Planck units. Okay? If it was bigger than that, we would have seen primordial gravitational waves by now. So it has to be less than this, and maybe much less. Okay? And it also turns out to just get inflation to work in the first place, you can't just put in purely vacuum energy, because then it would last forever. It has to be a temporary phase that ends, and this requires somewhat special dynamics, which I'll review later on. Okay? So again, these are slightly strange things. Now what you might say, and as I'll discuss for the next sort of while, is again, this standard cosmological model is based on general relativity. Okay, so I consider this to be general relativity in the sense that you can just add to general relativity, or you can include a constant and some dynamics that I'll review. And you're allowed to wonder, could it be that gravity is behaving strangely, that we don't have to do these funny, what at first sight look like funny kinds of things. Okay. So you're allowed to consider that as a possibility. So I'd like to explore that and see where that leads, if anywhere. Okay, so I say large distances because, again, I'm talking about cosmology here. Okay? We're talking about these accelerating phases affecting the whole universe. Okay? So particularly at late times, this is very large scales here, our whole universe. Now, trying to modify things at large distances is not an easy task. Okay? It might sound easy at first sight, but often in physics, there's a kind of notion of universality. So let's say this is representing many microscopic theories, many different kinds of interactions. And at short distances, okay, the language is to say it's in the UV. But anyway, at short distances, there are many theories. And often one has universality, that as you zoom out and look at things at larger and larger distances, many different microscopic theories look the same. Okay? And so in fact, that's familiar. It's like if you try to study say, the air in this room and try to study fluids, you don't need to be an expert on nuclear physics to worry about how the air in this room is behaving. Okay? We're looking at much larger scales than down at the nuclear scale. In fact, that fluid description will come back later on, quite literally. All right, so for example, let's consider not fluids for the moment, but say electromagnetism. So, people like to walk around with Maxwell's equations on them. And these Maxwell's equations seem like some very kind of sacred thing. Of course, electromagnetism was our first example of a theory that's compatible with special relativity. Okay, and in special relativity, it's convenient to lift from these 3 vectors into some kind of 4 vector, an A mu. That's the electromagnetic potential A mu. And then there's some current, J mu. Charge and current densities is put into this 4-component object J mu. And then the dynamics of the field is connected to this funny thing F mu nu, which is roughly sort of the kinetic energy associated with this field. All right, so in any case, just relativity forces you into, when you write it in a relativistic notation, it becomes extremely simple. All right, and for example, if you solve this thing, you know that if you have 2 point charges, the potential energy between 2 point charges goes like 1 over r, just from Coulomb. Okay, and then there's some constant proportionality. Now you might wonder, is there anything you can do to mess with this structure? Just say just as a theoretical exercise, could I play with this? Okay. Well, one thing you could do is you can do the following. So when you contract these funny looking indices like this, so F mu nu is a scalar. So it's a Lorentz scalar. And the square of any scalar is also a scalar. So is its cube, and so on and so forth. So the square of this thing is also a perfectly good Lorentz scalar. That means that this is perfectly compatible with special relativity as well. So you could add this. Okay? So there I've monkeyed with Maxwell's equations. Okay? Now, one thing to note, however, is that just from dimensional analysis, this f squared thing has units. So to make this dimensionally correct, you have to put a coefficient in front of it, L to the 4, where L has units of length. Okay, so it's a parameter of the theory. This L tells me how much I'm modifying Maxwell's theory. It's a parameter in the Lagrangian. And this L has some meaning. In particular, if you start probing physics on scales of order L, this guy is very important. On the other hand, if you probe physics on scales much bigger than L, indeed this guy is irrelevant. You just forget about it. Okay? And so that's coming back to this idea of universality. This L is some parameter that tells you which theory you're in here, but as you zoom out, you just get to this, you get to the t-shirt. So you might wonder, is there anything you could do to modify Maxwell's equations at large distances? So one thing you can do is this. You can turn on a mass for the photon. Okay? So there's some term here. And this thing, far from being irrelevant at large distances, becomes more and more important at large distances. So you give the photon a mass, for example, the potential energy between 2 charges has this exponential factor. So that radically changes things at large distances. Okay, so there is something you can do. So we'll come back to that. All right, so we want to build interactions, and the world is sort of built out of particles, unless you get down to, say, string theory or something. Essentially, the world is built out of particles. And they're quantum particles. They have some spin. Okay, and the spin is either 0, half, 1, 3 halves, 2, and so on. Spin has to be any half integer, and it could be more. Just I'll list the rest as ... We'll come back to that. And this spin, you recall, is a very physical thing. This is literally, in units of h bar, Planck's constant, it's literally the amount of angular momentum a particle can have. It has that exact value. Okay? And so it's sitting there spinning. Say a photon, which is spin 1, is sitting there spinning with an angular momentum of 1 h bar. Now what is important, and just from what I mentioned a minute ago, something very important is this issue of massless versus massive. And so this DOF means degrees of freedom, or the number of, if you like, polarizations that these particles have. Okay? And so quantum mechanics plus relativity actually forces this structure on you. Okay, so a spin 0 particle, well, it has no polarization. It's just 1 degree of freedom. A spin half particle, say an electron, can be spin up or spin down. So 2 polarizations. And that actually doesn't matter if it's massive or massless at this level. A photon is a massless spin 1 as far as we know. So 2 polarizations. Okay. But if it was massive, like the W boson, it has 3 polarizations. Okay? So the total angular momentum is 1, but if you project its angular momentum, say, on the z-axis, you may find 1, 0, or minus 1. 3 possibilities. And it goes on like this, okay? 4, 5, it just keeps going up like that. For the massless guys, which are zipping along at the speed of light, you can only measure their spin parallel, or the only spin that makes sense is parallel or anti-parallel to the direction of motion. So you always get 2. And so in particular, spin 1 and spin 2, we have these differences, which we'll have to worry about. Now, we have this whole menu then of possibilities. Right? If we want to build interactions, and in particular build some theory of gravity, we've got to pick from this set of possibilities. Okay, so one first of all thing to remember is that, let's say you have 2 objects, object 1 and object 2. Maybe this is the Earth and the Moon. It doesn't matter. And they're going to feel a force between them. The most leading order and the most important effect, the most important thing that can give rise to a force between them, is that they exchange a single particle. If they exchange multiple particles, that's generally less important. And there's just a fact that fermions cannot change particle number by 1 at a vertex. So you cannot exchange a single fermion. If you do so, it turns out you've messed up rotation invariance. However, you can exchange a boson. So for example, you all know that an atom can absorb a photon, can emit a photon. Boson number is not conserved in any approximate sense. Okay? So it has to be a boson, and generally its potential will look like this. If it's massive, if it's massless, you just drop the exponential. Okay, so if we want some theory of gravity, we can immediately forget about fermions exchanging, being the ones which are spin half and spin 3 halves, odd integer spins, odd half integer. We can ignore those for this discussion. It's these bosons, 0, 1, 2, and so on, that we have to focus on. And that degree of freedom business that I mentioned makes life a little complicated. Spin 0, however, is not. There's just 1 degree of freedom, as I mentioned. And if you like thinking about fields, you can describe it by some single field, a so-called scalar field phi. For spin 1, let's say you had a massive W boson, it must have 3 degrees of freedom, as I mentioned. And that can be described by a vector field, A nu. But for a massless, say the photon, you need to get down to 2 degrees of freedom. And so one introduces famously this identification. Say A mu is identified with A mu plus D mu alpha. So you say there's this whole family of vector potentials that describe the same physics. And that's what you need to do to get from 3 to 2. And this is a funny thing, actually, because if you, amongst this family of possibilities, if you make your favorite choice, to use the jargon to gauge fix, and then you transform this under a Lorentz transformation, A mu is actually not a good vector. Okay, so the dirty little secret that the vector potential of electromagnetism is not actually a good vector. And that makes life very tough to couple it in an actually Lorentz invariant way. You have to work really hard. And a similar story for spin 2. If it's massive, you can describe 5 degrees of freedom in some simple way. You don't need any identifications, it turns out. But for massless, you do. You have to get down to 5 to 2. There's this whole family of these H mu nus, these spin 2 fields with 2 indices. So again, it's going to be really tough to build a consistent theory like this. And this led, for example, Weinberg to, in the 60s, to give us this soft theorem. So for these massless particles, okay, to interact in a Lorentz invariant way with the most leading interactions, we'll come back to that, there are constraints on what the coupling can be. So imagine this is a matter particle here, this solid line, and the dotted is one of these bosons. Say you could think of it as the photon or the graviton, something like that. And kappa is the strength with which this matter particle sources, say, the photon, kappa, to spin S particle. For spin 0, if this guy is a spin 0, it's boring. You can do whatever you want. It's trivial to make it Lorentz invariant, as I said. For spin 1, famously, when you sum up all these couplings initially, they have to equal the sum of all the couplings going out. So conservation of charge. This is what you just have to do. That's an interesting thing, by the way. If you say a muon can decay into an electron, it tells you that the strength with which a muon talks to a photon must exactly equal the strength with which an electron talks to a photon. That's a kind of surprising thing. But it has to do that. As you keep going down the line to higher spins, the constraints get more and more and more severe. So when you go to spin 2, all these numbers have to be the same. And all these kappas here, so this is the strength at which you talk to the graviton, that's usually called the square root of g Newton. So that's the equivalence principle, as Weinberg showed in the 60s. Now, all the kappas are equal at spin 2. What's going to happen at spin 3? Spin 3, there's nothing you can do. Spin 3, you have to set them to 0. If you want a non-trivial theory, there's nothing you can do. And that goes for higher spins as well. Okay, so all these ones over here, we can forget about those. They're not going to play a role giving rise to long-range interactions. This spin 2 guy, okay, is very special. Okay? And as I just reviewed, all the couplings have to be the same. Comes from applying Lorentz symmetry to mass the spin 2 at large distances. I'll revisit that idea later on. We'll see if we really do need the Lorentz symmetry after all. Special relativity, if you like. And from this sort of hard-nosed point of view, I haven't said anything about curved space. It allows you to take, this is flat space, e to mu nu, and this is our spin 2 field, h mu nu, and kappa is the square root of g Newton. So that's the strength of gravity. If you just add these together, you can, it's kind of an exercise. You find that this thing has a metric interpretation. Okay, the g mu nu you can interpret as being associated with curved space. You didn't need to know it ahead of time. Okay, so if you like, you can say if I have a clock, okay, and I put it, say, near the Earth, just this consistency means that the graviton couples to every atom in the clock. Okay, all the same. Okay, so it's altering the rate at which the hands are moving because of this requirement. And it moves a little differently than if you put the clock far away from the Earth. We call it gravitational time dilation, so on and so forth. So we have curved space-time. And so in some sense it comes out of this rather than an input. Okay. These funny things like h mu nu and g mu nu, as I said, like a mu, and actually not quite good tensors or vectors. There are other related things which are called the Riemann tensor. And you can build some Lorentz invariant theory by combining them in some very special way. So this is called the Einstein-Hilbert term. Governs the dynamics of gravity. If I have a scalar particle, it has to talk to gravity through there's some factor of g mu nu, so on and so forth. If I have an electromagnetic field, it has to couple in some certain way. Okay. So it's a complicated computation, but you can derive this is just required. And by the way, if I have a scalar around, as I said before, phi is a scalar, it's just some boring spin 0 particle. The square of it is a scalar. The cube of it is a scalar. The phi to the 4, phi is a scalar, phi to the 4 is a scalar. So if you just say, write down everything that you can write down that's a scalar, in other words, compatible with special relativity, Lorentz symmetry, you can just write down a tower of these guys. So the scalars, you have lots of freedom. And this freedom actually allows you for a new phase to emerge, inflation. Okay. So let me explain that. Okay, so you just have your graviton, spin 2 guy, and spin 0 some one or more scalars. And as I said, just write down whatever you can think up. That's a Lorentz scalar. So there's no reason I shouldn't have a phi squared, a phi cubed, which you can picture as allowing 3 scalars to bang into one another. Phi 4 is 4 particles banging into one another. And they have random coefficients at this stage. They're just allowed. No one can tell me what their values are. And you add them all up, and in the field perspective, there's some function, v of phi. Okay? And if this function has a certain kind of shape, which turns out it needs to be rather flat in a suitably defined sense, then the field kind of gets stuck there for a while, and the universe, it acts as a kind of vacuum energy that causes the universe to accelerate. Okay, inflation. And then eventually it rolls down, and inflation ends. And that's good. We don't want inflation to last forever. And if you couple phi to other matter, at the bottom here it can decay into other particles. And particles we ultimately are made out of. Okay? So actually from this point of view, inflation is not some crazy thing that people just dreamt up. It's a bit like superconductivity. Okay? Even if you never had an experiment that you knew superconductors existed, if you just take the QED Lagrangian, which is quantum electrodynamics, and ask what does it allow? Okay? It allows for ordinary conductors as a solution, and then under certain conditions it allows for superconducting. So just the graviton with scalars allows for ordinary phases to occur as well as this inflationary phase to occur under certain conditions. It's just something that can happen. Now it does require very small interactions for this potential to be suitably flat, as I said, which you can try to motivate by saying there's some kind of symmetry associated with the field and approximate shift symmetry. Although from this perspective that would beg the question, why is there this symmetry in the first place? Or just maybe there are accidental cancellations between these guys that makes the potential suitably flat. Okay, so we're back to maybe just some accident happened. Okay? Yeah.
Will you think about partial couplings, like d-phi type couplings in this scenario? Or,
Well, you mean d-phi to the 4 and so on?
for example, since you have your shifts in
That's right, yeah. So certainly there's many other operators I can add here. So and many models of inflation exploit other kinds of derivatives and so on as well. That's right. But for simplicity here, I'll be just focusing on the potential. Okay. Okay, so that's one comment. And as I said, so you would have to, maybe there's some accidental cancellation or whatever it is that gives you inflation, wherever that may come from. And again, from this perspective, just a constant is as good a scalar as you could imagine. And then you'd have to put in the 10 to the minus 120, as I mentioned, to have a late time acceleration. And you may declare victory, but you might say, well, wait a minute. It's a little, we understand GR, but why does it have these fine-tuned cosmodule constant, 10 to the minus 120, funny inflationary parameters that give you a sufficiently flat potential? So maybe you could try to modify gravity. Okay. And as I said, this is not easy, right? We have a kind of a theorem, the unique Lorentz invariant theory of a massless spin 2 particle with leading interactions is general relativity. And by the way, I talk a little bit in a kind of quantum language. You might say, why is this guy saying quantum mechanics? It's not so important, though just as an aside, you can think of this as a quantum theory. Okay? For example, you can have fun computing graviton loop corrections between matter, and there's some definite force you can calculate that we had some fun doing. It's just a correction to Newton's law under certain so-called polarizable material. It's so small, forget about it, but you can compute it. Okay? So this is a good quantum theory as long as you stay at energies below the so-called Planck scale, about 10 to the 19 GeV. Low energies, you can compute quantum corrections, so they're ridiculously small. Okay, so if we want to get beyond gravity, so we could move beyond the leading interactions, you could add higher derivatives. Okay, so what do I mean by that? I'll give you an example. So this funny thing, the Riemann tensor, some more or less a good tensor, you could couple a pair of photons, or the electromagnetic field, directly to it. Okay? And if you have a bunch of particles, say the photon, the gluon, so on and so forth, they could all couple to gravity differently with a different coefficient, what I called C sub I. And there's some m to fix the unit, some mass scale. So you could just do this. And of course, famously, Einstein computed the deflection angle theta when light bends, say, past the sun. Okay, there's some famous formula for that. If you add this term to your theory, it's a higher order correction, there's a new correction to how it bends, and the correction to the bending angle divided by Einstein's familiar bending angle is set by this coefficient c, and then divided by m squared b squared, where b is the impact parameter. Okay. This is, usually a very small number, but you could write it down. And so what it would mean is that different particles with different c's get bent differently. Okay. So you wouldn't have the equivalence principle per se, you would have a kind of equivalence phenomenon. That when you go to large distances, which is the limit where you ignore this thing here, you get back to good old equivalence principle. But as you zoom in at least a little bit, depending on how small m is, or how large m is, you would see the corrections. Okay? So from this point of view, our slogan would become gravity equals curvature at large distances only. In other words, we'd have two different particles, say the photon and the gluon, they bend different amounts, but they both see the same space-time. So if you say gravity equals curvature, you have to have a caveat associated with that. Now let's say I just wrote this down for whatever reason. You could ask, could these corrections dominate? We haven't seen them, by the way. Of course, you would all know. So one thing becomes an issue, which is that of this thing called causality. Okay? So this is position and this is time. And these lines at 45 degrees in my units are the light, Minkowski light cone. So that's the direction light would move on, either to the right or to the left. Okay? If light was moving through the vacuum. Now let's suppose you have some material sitting here, and it's static in this coordinate system, so it just moves straight up, but it has some finite width. I've indicated this rectangle in gray if you can't see it. And if you send light along, okay, let's say you have a material, one of two things could happen. It could either be slowed down by the material, which is familiar, like light traveling through glass, let's say, or something really funny could happen, it could be sped up by the interactions with this medium. Okay, so it will be superluminal. Now, in general relativity, okay, let's recap what happens. Because if you like, in general relativity, we interact, so to speak, with light bends by the sun. Does it speed it up or slow it down relative to what would happen if there were no sun? Okay? And it evolves under this so-called geodesic equation, which I can write in this form. So k mu is the form momentum of the photon, and you contract some indices and you have to get 0. That's just general relativity. And you can repackage this thing by writing g mu nu as the flat space eta mu nu plus the correction from gravity. And you find that the square of the photon's form momentum is some funny integral. Okay? It depends on the strength of gravity, g Newton. And there's some integral over this thing, T mu nu, which is the energy momentum tensor of matter. Okay? And this quantity is in fact always positive whenever you have matter that obeys a condition known as the null energy condition. The null energy condition is something obeyed by all forms of matter we know about. For example, the whole Standard Model of particle physics obeys this condition. So whenever you have ordinary matter that the light is passing by, this thing is always positive. And you might say, what's the consequence of k squared being positive? This is related to the speed at which this guy is propagating at. So in fact, k squared being positive translates into this thing always being subluminal. So it gets slowed down by bending past the sun. And that's, in fact, the Shapiro time delay, which you may know about. Okay? And then everything's causal. Everything's slowing down. There's nothing funny happening. If you turn on this thing, this is another thing I could just turn on, as I mentioned a couple of minutes ago, coupling directly to Riemann. It's a little more complicated, so don't worry about the details too much. But you find that from this particular interaction, this k squared is plus or minus some quantity. And the plus or minus is for the two different spins or polarizations of the photon. And it depends on the strength of the Riemann tensor and so on. So what happens is if you turn on this thing, one of the polarizations of light is subluminal, and the other polarization is superluminal. Okay? So this is very bad, right? Because let's say down here, like I'm holding, this is a laser, so I press the button of the laser and the light comes out. And I've designed my laser so it has a polarization which is the blue line. I can do that. And then over here it does something. Let's say it sets off a bomb. Okay, over here. Well, this is a nice Lorentz invariant theory. So what you can do is you can boost to another frame of reference. And in another frame of reference, this blue point here can be made earlier in time than when you press the button over here. So you upset causality. Okay? So in fact, this Lorentz invariance makes causality rather dangerous. You have to be careful with what interactions you turn on. And so in fact, this idea is not just restricted to some funny coupling to the photon. You can couple to all sorts of things, scalars, fermions. As long as they have these sort of higher derivative couplings to gravity, we could show with McCullen-Sandora that these things are always acausal. Okay. So in other words, they can never dominate over the Shapiro time delay. You have to make them really, really suppressed. And you have to give them really tiny coefficients. Then life is okay. So you can never change gravity too much or you'll screw up causality. Okay. So this spin 2 guy is special, and it has to be dominated by the leading interaction, which is general relativity. All right. So what else can you do? Well, you could say, well, let's include other spins instead of spin 2. Right? So we go back to our menu. Say, what about this spin 1? Okay, well, spin 1, there's not much you can do, really, because you're just guaranteed that if you look at big conglomerations of matter like the moon and the earth, that they generally become neutralized. Okay? So you get big objects that are neutral, and because opposites attract and likes repel, so the spin 1 guys become less important at large distances just naturally. For spin 0, we could study the massive or the massless, but they're kind of continuously connected to each other because they have the same number of degrees of freedom. So we can discuss that in one go. Now, the usual philosophy here that people say is, let's try to mimic what happens for gravities, for usual gravity, spin 2, where this spin 2 field h mu nu couples universally to the energy momentum tensor T mu nu, which I said is required. So for a scalar, one imagines, well, I'll just take a scalar and couple it in a similar way. To contract indices, you couple it to the so-called trace of the energy momentum tensor with some coupling like called kappa super phi. And these are usually called scalar tensor theories. So you put this in by hand, and this can have long-range effects, modifies gravity. And by coupling universally, you satisfy the weak equivalence principle. Well, never mind principle, it forces things to fall at a universal rate, say not for non-relativistic matter. So for relativistic matter, the trace of T mu actually is 0, turns out. So this term won't affect the bending of light. And so what you mess up, there's an effective G Newton, which is actually a combination of these kappas and kappa phis for matter on Earth, the non-relativistic stuff, that is then different for light that's being bent by the sun. Okay. So the bending of light, if you fix units where this total is the regular G Newton, the light bending is affected. And then the only way this is consistent is if this coefficient kappa is super small. In fact, it needs to be about at least 3 orders of magnitude less than the usual gravitational coupling. Remember, kappa is the square root of G Newton. Okay, so you introduce this scalar, and then you just say, well, let's just forget about it. Let's make it super small. Okay, which doesn't sound so interesting. But from the perspective that I try to convince you of, right, we don't, this first, even before worrying about that, the fact that phi couples universally seems a bit strange. I told you scalars can couple however the hell they like. So it's a bit mysterious as to why it even couples universally in the first place. For spin 2, it's not. This is required for consistency. Now, from that perspective, you might say, this is actually a problem. Right? Couldn't I have some light scalar that was coupling non-universally? Why is it that we don't see this guy in the first place? That's would be screwing up observations, making things fall at different rates if I allowed for generic couplings. Actually, quantum mechanics explains that, arguably. Okay? So the moment you have some scalar and it couples to matter, which is what we want to propose, all right, well, that's the idea, right, for it to mediate some force. The moment it couples, you can do these loop effects where the matter particle that it couples to comes in and out of the vacuum, the particle and antiparticle, and it generally gives corrections to the mass of this thing. Okay, and in this example, it would scale like the mass of the fermion, the strength of the coupling kappa, and then lambda uv, which is the momentum you integrate up to in the loop. So you've got to cut off the loop somewhere or things diverge. Okay? And so this tries to make this scalar particle heavy. If it's heavy, we could just forget about it. It only would, even if it was there, it would mediate such an exponentially, its effects would be exponentially suppressed at large distances anyway. So if you want cosmological effects, let's say, so the Compton wavelength is, let's say, today's Hubble scale, 10 to the 25 meters, you'd have to cut off this loop integral, for example, down at like 10 to the minus 7 electron volts. Okay. On the other hand, if you want a theory to make sense to high energies, it implies that this scale is very heavy. And so that's why we haven't seen it. So it's all consistent. Okay. Now, on the other hand, you could say, the reason it's light is because of this thing called a shift symmetry. This forbids an m squared phi squared term, a mass term. But if you impose a shift symmetry, it prevents you from coupling in the first place. So then again, it would be irrelevant. So it's all self-consistent. Okay. So it's very difficult to make sense of these scalars. They naturally just want to be sort of heavy, as I said here, or irrelevant. Okay, they can be massless naturally, but then they don't mediate long-range forces. Okay, so one can quickly, you could give up the idea of it being massless. That's massive spin 2. Okay, so this one over here. And this one's kind of an interesting story. So the next few minutes is kind of revision. I can't claim to have added anything to this. So just as you want the massless spin 2 guy, as I said, has to couple universally, just to be compatible with special relativity. Massive, you think you could do whatever you want at first sight. It turns out you also have to couple it universally because there's some lurking problem in the theory called a ghost. And to avoid this thing called a ghost, you have to couple it universally. This is very good if you want to promote massive gravity. It has to do this just like the massless guy does. This is a surprising result, actually. So it's immediately compatible with the weak equivalence principle tests. But what about its extra dynamics? This massive spin 2 has 5 degrees of freedom. Right? If you measure its polarization, you could get +2, +1, 0, -1, -2. 5 possibilities. And the 0 out of that is kind of a longitudinal mode. as opposed to the transverse modes of, let's say, gravitational waves. And this most longitudinal mode actually turns out to couple like the thing I mentioned a minute ago, and it happens automatically, not by fudging. It couples universally, as I mentioned up here. Okay, so that sounds good, except there's a real problem. Okay, so these scalar modes, the longitudinal part of this guy, interacts with itself. And you may know this from the case of spin 1. So if you imagine these are W bosons, you can throw longitudinal W bosons at one another. And a funny thing happens, that the strength with which they scatter off one another grows with energy, grows like E squared. And the probability grows like this. So when you throw W bosons at each other at very high energies, the probability of them scattering, according to quantum mechanics, gets bigger than 1 at some scale. And you have to cut off the theory. At some scale it goes like this, and that turns out to be a TeV, literally for W bosons. And then you introduce the Higgs and you cure this disease. Okay, so that's an old story. Well, for spin 2, this massive spin 2, it's similar. It has some self-interactions. It's a different type of interaction, but there's some self-interactions. So these massive W bosons, these massive spin 2 particles, say the massive graviton, it will bang into one another, and its scattering amplitude grows like energy to the 6. But high energies, the probabilities are just going crazy. And to cure this, you have to cut off your theory, but now you have to cut it off not at a TeV, and then put in the Higgs with a mass less than a TeV. It turns out the scale here is 10 to the minus 13 electron volts. Okay? If you put the graviton's mass to be the Hubble scale, which is about as big as it could possibly be, since we've never seen its effects. So this theory falls apart at extremely low energies from this self-interactions. And so then you would effectively have to lift this with some funny Higgs mechanism to the massless guy anyway, just like the Higgs does in the Standard Model, where the W's and Z's in some sense are secretly massless at high energy. Literally massless at high energies, in fact. Okay, and then it turns out that these funny interactions that make it compatible with light bending, there's an associated acausality lurking in this theory as well, which I don't have time to discuss here. Okay. So it's very difficult to make sense of this massive spin 2 guy. All right. Now the one other thing that's lurking in my list of assumptions up there is the one thing I always, for my whole life took for, well, since I learned a little bit about physics in college, I always took for granted the idea of Lorentz invariance. Okay? So what you might say, okay, that's the one thing that I started with, right? That the Weinberg theorem appeals to, so on and so forth, and so many of these consequences follow from, as well as some consistency with quantum mechanics. So what if you just give up the Lorentz invariance? Okay. Right, we're desperate here to explain 10 to the minus 120, so let's just try something. Okay. So again, once you assume Lorentz invariance, as Weinberg did, there's all these very, as you go to spin 1 and indeed to spin 2, you get very strict conditions that must be obeyed. For example, the equivalence principle. Okay, I don't have time to explain it, but if you give up the Lorentz invariance, but you don't give up everything, if you just demand that your theory is still local in some sense, this is work again with McCollum-Sandora. And by local, I mean that just the most basic notion of locality. So I don't want it to be that if I move an electron here, I instantaneously move an electron in the next galaxy. Okay, I just want to avoid instantaneous action at a distance. And just to avoid instantaneous action at a distance, you once again get loads of freedom with scalars. Spin 1 is actually, you can still prove, turns out global, not local, conservation of charge. It might sound a little bit surprising, but for spin 1, you know, if you recall, you have this thing, the Coulomb potential, and then there's the vector potential A. And the Coulomb potential, you may recall, is instantaneous. It's non-dynamical. So which really wants to give you instantaneous action at a distance. And then you have to combine this instantaneous thing, the Coulomb potential, with the vector potential A in a very special way that you may recall if you studied electromagnetism. And their instantaneous effects cancel out almost magically. And it seems like that's all to do with Lorentz invariance. Okay? But actually, even without Lorentz invariance, if you just demand locality, you can still make it, if you just demand locality, they still have to come in a very special way that's enough to ensure charge conservation. Okay. Now for spin 2, life turns out to be, once again, even harder. So if I want a local theory of spin 2, just like the Coulomb potential is non-dynamical, The Newton potential is non-dynamical. It's associated with the 0, 0, the H00 part of this h mu nu thing. Okay? And this guy is non-dynamical. And it's trying its best to give us instantaneous action at distance. And even without knowing about Lorentz invariance, if you just want to remove that, you have to combine the H00, the H0i, and the Hij in some very special way and build up this h mu nu. And the only way to make it local, it turns out you need these conditions. So this is the sum of the couplings times the energy of the particles in some process has to be conserved. And this is those same couplings times the derivative with respect to momentum of the energy squared has to be conserved. So we could prove this. And if you solve this pair of equations, it turns out it only has one solution. And the solution is that all these kappas have to be the same. So once again, you get the equivalence principle. And this E squared, which a priori could have had any dispersion relation in the world, so any relationship between energy and momentum, the only one, you can probably see it, that the only way it can work is if the E squared goes like P squared C squared plus M squared C to the 4. So for example, if you differentiate, then you get a factor of P. Momentum is conserved, so that's how you make it consistent. And where this has to happen for every single particle because the couplings have to be universal. And it turns out this has to be exact if you want some strict notion of locality. Okay, so there cannot be like some P to the 4 corrections or whatever you might imagine. And the one little twist beyond what you're used to seeing is that the C here, I wrote C sub G for graviton. Without the graviton, this doesn't work. You can have whatever you want up here. The moment you throw in the graviton, you need this, and then it has to be true for every particle. Okay. So this spin 2 guy is so clever that if you just demand your theory is local, in fact, you actually need special relativity. And once you have special relativity with spin 2, then you're back to the story I've already gone through. You get general relativity for free. All right. So it seems these large distance modifications to general relativity don't make a lot of sense. I mean, maybe you can start giving up causality or locality or something, but if you stick within that framework, it's very difficult. It seems to be impossible. And so you could ask, what does the data favor now? Okay, so there's a very interesting story. So if you look at, say, this is some simulation at large distances, okay, and this is the so-called Millennium simulation, and these are all sort of individual galaxies, okay, and you'll notice that when I started the simulation, at the initial time, things look very homogeneous on large scales, but as you zoom in, the density contrasts get larger and larger and larger, okay? Okay, so in fact, as you get into sort of a scale of order megaparsecs or so, there's a sort of an order 1 density contrast from one region to the next, so you have clusters of galaxies. Okay. And now you might say, can you build some kind of consistent theory, a sort of perturbation theory, to analyze the evolution of this system? Okay. And you would say, well, clearly I can't, because when I'm down at this scale, perturbations, things are completely nonlinear. Okay, so it seems very difficult. And these nonlinearities here will affect what happens at large distances because of mode-mode coupling. Okay, whatever happens at short distances at some level affects what happens at large distances because all the modes are coupled. Okay, and so then we made sort of some progress on this so-called effective theory of large-scale structure. Okay, and I'll just mention some old references. There's new work, so for example, Ashley and others are experts on this and done some beautiful work. And so, for example, the idea here was that when you're at large distances here, you sort of divide up your modes between what happens at large distances where things are kind of perturbative, the fluctuations are small overall, and then at short distances, the things are very nonlinear. So you say, well, those are my so-called UV modes. So this decomposition is very useful, and the large distance effects actually incorporates interesting physics like the baryon acoustic oscillations, these peaks and troughs that I mentioned earlier. So you can capture something interesting. And this short distance physics here, what does it do? Well, it has, by mode-mode coupling, has some impact at large scales and reorganizes it into some kind of fluid. And this fluid has parameters associated with it, such as viscosity. Okay? And so that is a, sort of an analog of our, this parameter here I mentioned, right? Some L to the 4 parameterizing short distance effects, say some leading short distance effects. In this description, something like the viscosity is telling you some information about what's happening at short distances, and it shows up in the fluid description at large distances. Okay, and so then one can here's some result. Okay, so this is sort of these wiggles that I mentioned before. The power normalized in some sense as a function of wave number, where the dotted is the linear theory. The red here is what you would get if you didn't think systematically in terms of this idea of separating out modes, this sort of effective description. So that's what the first nonlinear correction predicts. But then if you do it systematically, including this like viscosity and sound speed and so on, there's some curve which is the blue one here at this leading order, and then black is really, in this case it's a simulation, but it's compatible with data. So this level gives I think some understanding as to the shape of these things, right? So these barren acoustic oscillations here, as I said, are affected by how the universe expands. And here one is doing the computation in the case of a cosmodule constant, and it's consistent with a pure cosmodule constant. Okay. And of course, as I said, there's been much more work since then. So both theory and observation suggest that the only consistent theory of gravity at large distances is general relativity. And so finally, we come back to what I mentioned earlier on. We have to deal then just with these things. We have to have a funny number for the cosmodule constant, and inflation has some funny dynamics associated with it. Okay? And you could ask, can you understand that? And so, as I mentioned before, inflation is just some phase that can occur, like superconductivity. But suppose you don't have one scalar, you have many scalars. Okay? Then just because of locality, if you like, or Lorentz symmetry, you can just write down all sorts of terms. So not only can, say, 3 phis bang into one another, but 3 different types of phi particles can bang into one another, 4 and so on. It's just allowed. Lorentz invariance just says these are allowed. Okay? Or if you like, locality is enough to prove this. Okay? So now you have a whole pile of parameters, these gammas, these lambdas, gazillions of parameters come in if you have many particles. Okay? Well, not quite gazillions, you know, say hundreds or so, or some number of parameters. And then you just, if you allow me for random parameters, then it's just combinatorics that says that this builds some funny potential function, and it's going to have many, many maxa and minima. Just combinatorics. Okay, if you just stare at a random function with random parameters. And the number of vacua ends up being exponentially large, okay, in the number of fields that you have. Okay. And so then somewhere here you can randomly find places where you get this very small cosmodule constant, and at near some random peaks, let's say, you could get inflation. Okay, so it's just combinatorics. So that's a nice idea. You can ask, can you embed that idea into microscopic physics? Okay. Especially for inflation, we're getting at very high energy densities here. And our best idea about the ultimate microscopic physics incorporating gravity and quantum mechanics and string theory, right? And arguably the best corner of this is something called the type 2a corner of string theory. Okay? And this has a certain set of standard objects within it that are allowed by consistency. Okay? And it has, at first sight, the ingredients that should make this thing work. Okay? So it's this funny theory. It lives in 10 dimensions. You compactify 6 of the dimensions to make them small. Okay? And then the compactification, there's many fields associated with how this compact space is organized, its size, its shape, and so on. And this turns out to be hundreds of these scalars, kind of ingredient that I just mentioned. And then you can have these sort of generalized electromagnetic fields can actually wrap around the compact space, so-called fluxes. And these fluxes determine, roughly speaking, these coefficients, these gammas, these lambdas, and so on. You have all these ingredients showing up. Okay? And then indeed you get some exponentially large, right? N to 100, N to the 1,000 different type of potentials. Okay? Just from this, just all the possible ways you can compactify. Okay? So this is exactly what you would want. Right? So that's fine. And then we actually explored it. Right? We went the step beyond his set of words to actually do the computation. And so at least in this corner of string theory, we could find actually this is not what happens. So we could prove this no-go theorem. That in fact nowhere, despite the fact that we really do have, these things are all facts here, okay, so there really are exponentially large number of vacua, right, 10 to the whatever, 500, and there's a huge number. In this corner of string theory at any rate, not one of these points actually has, the vacuum energies are all negative. There are many minima, they're all negative, so not one of them accelerates. And while there are many regions that are positive, the potential doesn't turn out to be flat enough to support inflation. So you get neither early universal or late universal acceleration, at least in this corner of the theory. Maybe it works somewhere else in the string landscape. I don't know. Okay, so to conclude then, as I argued, general relativity seems to be the only consistent theory of gravity at large distances, with these kind of theoretical considerations. And furthermore, including pure vacuum energy and plus inflation is sort of favored by the data, it seems. And there's this nice idea that's just combinatorics that says if you combine this with multiple scalars, let's say hundreds of scalars, you hopefully could explain the fine-tuning where the cosmological constant is 10 to the minus 120 and you have inflation and so on, just by the presence of many vacuum and many structure in this potential landscape. But as far as I can tell, this has yet to be embedded actually in microscopic physics, like string theory. Okay, so there is still much work to be done. All right, thank you for your attention. Question?
When you want to modify the theory of gravity, can you consider this massive particles with spin higher than 2?
So you want massive n higher than 2. So as far as I can tell, that's also going to be inconsistent. I mean, massive spin 2 already has causality problems. As I said, massless higher than spin 2 is inconsistent. You can't even write that down. If you had, say, massive spin 3, it's difficult to make. So I think probably you can't make sense of it. I don't have a direct proof. But the theory at any level is going to become strongly interacting at some very low scale. That's still going to go through. And so you basically, if you want the theory just like massive spin 2 to make sense at high energies, these massive guys have to go over into some massless guy. And then the massless guy doesn't make sense. So there's kind of an indirect proof. So the thing that we are familiar with is, of course, if you look at, say, hadrons or something, you can have particles of high spin. Okay? But the descriptions of those particles, say you have a massive spin 3 particle, some hadron that you find in the lab, that's a well-defined particle, okay, as I called it, a hadron, so long as you stay at energies roughly below its mass. Now, if you want large distance effects, particles that mediate long-range interactions have to be really, really light. So now you want to say, let's say you want it to be Hubble scale, which is 10 to the minus 33 electron volts. Not much good having a theory that only makes sense up to 10 to the minus 33 electron volts. If you want it to be higher than that, in the analogy of the hadron, you have to replace it by something else. So the hadron has to be replaced by QCD. Okay? So you have to do something similar to that. Now maybe there's some loophole, maybe there's some funky theory of massive spin 3 I don't know about, but roughly that's the way it goes. I think maybe Ash.
Yeah, I was just wondering, you said that if it was a massive graviton, it had to be, the cutoff scale would be very low. But what's the problem with just having an EFT at low energies that describes massive photon just to be completed to the standard model?
Okay, so so for the graviton. So there's two issues. One, I didn't go into it in any detail, but one issue is that guy has problems with causality. Just that even within the low energy theory, in particular within the low energy theory, it has problems with causality. But even if you didn't care about that, and you just said, well, I have a theory whose cutoff is 10 to the minus 13 electron volts, beyond that scale, you basically have to replace this thing by essentially the massless graviton anyway. But okay, maybe you can live with a theory that for some reason we've not seen. There's some crazy physics that happens at 10 to the minus 13 electron volts that we've never observed. I guess that's a conceivable possibility. I'm not really sure what that is. And let me say that every attempt that people have made to try to provide the UV completion, no one has ever found it. And the reason that doesn't seem to exist is because it has these causality problems. You can't UV complete acausal theories into causal ones. It just doesn't work.
So, we know that in a slower inflation, space-time is roughly de Sitter. So I think in de Sitter space, we have more different representation for particles, something like partially massless. So we consider that kind of setup for this multiplication.
That's right. Yeah. Okay. I didn't really talk about that. So that's right. It is conceivable that there may be a loophole. So there may be some option there. I mean, so you mentioned inflation, but your theory has to be consistent down to today, for example. So you have to find a loophole from the fact that today we have a cosmological constant of 10 to the minus 120, And you're right, these arguments, these sort of Weinberg type arguments are rigorously defined in asymptotically flat space, and that's not quite true.
Right.
So somehow having a Hubble scale at 10 minus 33 eV has to upset this result. So maybe there's a loophole there. It's not clear to me how you can get much juice out of 10 to the minus 120. It's pretty damn close to zero, but maybe there's a possibility.
I think there's a recent paper on this partially.
Right. Yeah.
We can talk.
I was curious why you threw out long-range effects. You were saying only local effects, and you've basically thrown out entanglement, things like that. Why can't it be long-range effects?
Do you mean when I was talking about getting relativity, like I said I wanted my theory to be local?
Exactly.
Okay, well, there I guess I have in mind that, I mean local in the sense that I don't want to be able to instantaneously send a signal from one place to another.
But what if it happens?
But just to address your issue of entanglement doesn't allow us to send information instantaneously. So in the usual world, all signals are still less than the speed of travel slower or less than or equal to the speed of light. So you cannot use entanglement to send signals faster than light. I don't know if you can do something funky with a wormhole or something, but usually entanglement does not allow us to do that in some ordinary sense. The broader question of what happens if I just forget about locality altogether. Certainly if you have Lorentz invariance and you give up locality, then you're in trouble, because then you can boost the frames and screw up causality. If you give up Lorentz invariance and locality, there may be a way of building a consistent theory that way. That's true. So I did have to put in something. You can't get something out of nothing. So I did have to put in locality. But I will say that what I'm talking about is perfectly consistent with entanglement. Because I just don't want signals to propagate instantaneously. But I can have entanglement.
Oh yeah. What is preventing to generalize your no-go theorem to any string theory? What is the ingredient in the type 2 that is important?
The main ingredient would be me to have a few more neurons in my brain to try to improve this. I mean,
Aren't there efforts to uplift the potential to consider?
There are many attempts along these directions, but if you unpack the details of that, you find there's always problems. So I have not seen any consistent control.
I mean, to rule out the entire set of string theory would be an exceptional result.
Yeah, so I don't think I claimed that here. I said in this corner, which is where in this particular corner I'm looking at, is where all the ingredients are under control. So every time that people that I've seen, you could get different opinions from different people. What I've seen is that the models that seem to give you de Sitter space are always appealing to an ingredient that when you look at it, you find it's not really under control. The theoretical construction is not under control. So we went to a corner of the theory where we for sure everything's under control. And maybe it's so well understood that it's too boring, and that's the reason it didn't happen. So maybe you have to be in the hard regime, and then things may work out. So my guess is it works out, but I'd like to see it done concretely with complete calculation with all your errors under control. Because you can't compute things exactly, unfortunately. Yeah.
Last question for Dick. Oh, okay. So I think you can use fermions as mutators depending on how desperate you want to be. It depends on the mass scale associated with. So, like for example, back in the 40s, before they knew about neutrino scattering, they had neutrinos scattered mediated by fermions. And so at the loop level, desperation.
Right, but you can't get a 1 over r squared force there, can you?
That's right. You have to choose the mass scale correctly.
No, but even if you make the mass smaller and smaller, it's still not 1 over r squared.
It is not.
But that's...
There's a range of effectiveness. Again, it's a matter of desperation.
But also will not be a macroscopic field, right? Because you cannot, by the Pauli principle, you cannot pile up many of these terms to create a macroscopic. That's a different...
But you could probably get like a 1 over r to the 4 force or something like this.
So for
I mean, you can have pair of fermions in a loop. And that gives you, I don't know, 1 over r to the 4 perhaps, I'm not sure.
Well, anyway, so old particle physicists from like the 40s and 50s used to play around with this one before they knew about such scattering. And now the question is, well, you have to do like effective operators, you have to do the mass scales, and you can get like longish range scales, but it's from old 1940s, 1950s papers. So.
Okay.
Anyway,
I'll look at
again,
it.
it's a matter of desperation.
Okay.
And on that really uplifting note, let's thank Mark again for a really interesting talk.